Assalamu alaikum. I am Ayaz and today we are going to explore differential equations of higher order. This is going to be an introductory lecture, and in the coming videos I will be solving problems and examples. So let me write our topic: differential equations of higher order. So this is our topic of higher order. So first of all, we will go through the definition of linear differential equation of order n. So let me write the expression. In out of x dn y over dxn plus a1 of x dn minus 1 y over dxn minus 1 plus an minus 1 of x. This is my dy over dx plus this will be plus an of x y equal to f of x. This is my equation number 1, or I can write this expression like this. E naught of x y prime plus e1 of x yn minus 1 plus an minus 1 of x y prime plus an of x y is equal to f of x. So we can write in two ways. The second expression is more convenient, so I will use this expression throughout my lecture. So this is basically what I did here. This is basically another way of representing derivative. For example, yn. So yn means this is equal to dny over dxn, means nth derivative of y with respect to x. Similarly, if I write y prime means first derivative of y with respect to x. Okay, so I hope now it's clear to all of you. This is basically linear differential equation of order n in the dependent variable y and the independent variable x. So dependent variable is y and the independent variable is x, where a naught of x, a1 of x up to an minus 1 of x, an of x and f of x, they are basically functions of the independent variable x, and a naught of x is not equal to 0. So this is important. A naught of x, this is not equal to 0, because if this is equal to 0, like a naught of x equal to 0, then the order of this differential equation will go down. Then the order will decrease. Okay, so this is the reason that a naught of x is not equal to 0. Now if I let me write another equation. So I can write a naught yn plus a1 yn minus 1 plus up to so on an minus 1 y prime plus an y is equal to f of x. Uh, can you find the difference between equation number 2 and equation number 1? So this is my equation number 1. Okay. So the difference between equation number 1 and equation number 2 is that equation 1 is basically linear differential equation but with variable coefficients. So these coefficients, they are basically variables. However, in equation 2 we can see that these coefficients, they are not variable. They are basically constants. They are basically real numbers. So a naught, a1 up to an minus 1, an. These are basically real constants. Real constants. Okay. So first of all, we will focus on equation number 2, and we will solve a couple of questions, and then we will move to equation number 1. Let me write equation number 2 again. So this is like a naught yn plus a1 yn minus 1 plus an minus 1 y prime plus any. This is equal to f of x. This is my equation number, I would say, a capital A. This is my equation number capital A. So how to find the solution of this equation? Solution of equation number A. So how can we find the solution for this equation? So in order to solve equation number A, we shall first consider the equation. So I'm going to write, in order to solve our equation A, in our equation A, we shall first consider the equation. First consider the equation, and that is a naught of yn plus a1 yn minus 1 plus up to so on an minus 1. This is y prime plus a and y equal to 0. So this is equation number B. So in order to solve A, first what we do, we will basically write the left hand side and equal to 0. So now this equation B is called homogeneous linear differential equation of order n. This is called B is called homogeneous linear differential equation of order n. So solution of B, sorry, it's B. So solution of B is usually denoted by YC, complementary solution, or you can say the general solution of equation B. Okay. However, the solution of equation A is basically YC plus YP, and which is basically equal to y. So this is basically a complete solution, or the entire solution of equation A. Means it has two parts: yc, which is basically the solution of general solution of homogeneous equation, and yp, which is basically particular solution. So yp is basically yp is any particular solution, is any particular solution of A, and this is called complementary solution. Complementary solution, or maybe you can say general solution of P. Okay, and this whole basically y is equal to yc plus yp. This is called general solution. This is called is general solution of A. This is our general solution of A. It is important to understand that whenever you try to solve this equation, first of all, what you need to do, you need to write the left hand side, this expression equal to 0. So when you write this expression equal to 0, then now this expression is called homogeneous linear differential equation of order n. So if the right hand side 0, then this equation will become a homogeneous differential equation. Now our next target is how can we write yc? Okay, so rule number one, or you can say case one. Case one is when the roots are distinct and real. Distinct real roots. Let m1, m2, mn be n distinct roots. So in that case, yc will be like yc is equal to, so look, there are n roots, so I will take n constant. So the first constant is c1, and then I will take e, and I will write first root m1 with x, plus for root m2 I will take another constant, which is c2 e raised to power m2x, plus up to so on. For mn I will take cn, and I will write e raised to power mn x. So this is the way to write the expression for yc when the roots are distinct and real. Here c1, c2 up to cn are arbitrary constants. Arbitrary constants. Example: if m1 is 2 and m2 is 3, now I have two roots. One is 2 and the other is 3. So yc will become c1 e raised to power 2x plus c2 e raised to power 3x. Why did I write x? Because this is my independent variable. Okay, so at c1 and c2, because there are only two roots, so I will take just two constants. These are basically arbitrary constants. Case 2. repeated real roots. Repeated real roots. Let m1, m2 up to mn are repeated real roots. That is, means if they are repeated, it means they are same. It means all are equal. m1 equal to m2 equal to m3 up to mn. In that case, my yc will become yc is equal to. So look, there are n roots and they are basically same. They are repeating, okay? So I will take n constant. So c1 I will write like this plus c2x plus cnx n minus 1. E raised to power m1x. Basically, this is my c1, and here I can write this like x raised to power 0. Okay, so x raised to power 0 is basically 1, so we don't need to write x raised to power 0. So you can start from c2 x raised to power 1, c3 x raised to power 2, and up to so on, the last constant in x raised to power n minus 1. Okay. For example, let m1 is 3, m2 is 3, m3 is 3. So I will write yc like, now I have 3 roots. Okay, all of them are same, but I have 3 roots. So I will pick 3 constant c1 and x raised to power 0 plus c2 x raised to power 1 plus c3 x raised to power 2. Okay, let me write x raised to power 0 over here. And then e raised to power 3x. So root is basically 3, so e raised to power 3x. And this can be written as yc is equal to c1, x raised to power 0 is 1, okay? So I'm just writing c1 plus c2x plus c3 x raised to power 2, and this is e raised to power 3x. Case 3. Okay, so the last case is complex roots. Complex roots. Okay, for example, I have m1. My m1 is a plus iota b, and m2 is a minus iota b. So this is b. Okay, I can write like this: a plus minus iota b. This is basically real part, and b is imaginary part. So now you need to understand how we write yc for complex roots. So yc is basically c1 sine bx plus c2 cos bx, and then e raised to power ax. So what I did here, I picked sine and cos, and this imaginary part, this is imaginary part of the root. Okay, so this will go into angle of sine and cos. So imaginary part is b, it will become sine bx. Imaginary part is b, it will become cos bx. So I will take first one constant with sine and the other constant with cos, and then the real part, this will go into the power of exponential. Okay, so there is no restriction. You can write this expression like this: yc is equal to c1 cos bx plus C2 sine bx. So you can replace, you can switch sine and cos. It's up to you, okay? So it will not be a problematic if you write cos first and then sine. Let me give you an example. I have roots. The first root is minus 2 plus iota, and the second root is minus 2 minus iota. And I can write these two roots like this, minus 2 plus minus iota. Now, real part is minus 2, and imaginary part is 1. 1 means the coefficient of iota. Like I can write this expression as minus 2 plus minus 1 iota. So this 1 is my imaginary part and this 2 is my minus 2 is my real part. Now I can write this as yc as, I will write c1 and sine 1x, sine 1x plus c2 cos 1x and e raised to power minus 2x. And this expression can be written as yc is equal to c1 sine 1x. This will become just x. So I will write sine x plus c2 cos 1x. This will become just x cos x raised to power minus 2x. So these are the methods to write yc. Hope for the best, and I will see you in the next video.